Here we go. We're doing states of matter. Today's going to be section 1, gases. That's what's on the slate for today and tomorrow. Gases has 1s in the middle, not 2. There's no s in gases. It's the other way around. Think about it. It'll come to you. Someone. Oh! All right. Okay, so there was once this TV show back in the 90s, and the science teacher gave this boy a 2-liter bottle of Coke that was empty, and he said, write a report on what's inside the bottle. The bottle was empty, and the kid could figure it out. Finally, at the end of the episode, he goes, oh, it's filled with gas. End of story. Really exciting. So gases are made of molecules. The only gases that are not made of molecules are the noble gases. The final column, helium, neon, argon, krypton, xenon, radon. Those are all atoms. When you fill up a balloon, that is made up of atoms of helium. But with every other gas, carbon dioxide, water vapor, carbon monoxide, nitrogen dioxide, nitrogen gas, those are all molecules, which are more than one nonmetal bonded to each other. So you guys can likely, if I were to show you a solid, a liquid, and a gas, you would likely be able to identify the differences between them. So for instance, if I drew a solid, you don't need to write this, just pay attention. You know, that would be a solid, and I could put it inside a larger container such as this. And then if I had another container such as this, and there was some sort of fluid in there, that could be a liquid. And then if I had a container that appeared to be empty, that would be the gas. Well, all the states of matter have different properties, and that's what we're going to be going over the next 2 weeks, that are just inherently descriptive of what makes up those substances. So today and tomorrow is designated for gases, okay? All right, here we go. Let's talk about the kinetic, molecular theory. Kinetic means to move. Remember that all objects in motion have kinetic energy. So when gases are moving through an open space, they possess energy. The kinetic molecular theories describes the behavior in terms of particles in motion. Gases have the greatest kinetic energy. Of the 3 states of matter. The reason why gas molecules are not bonded to gas molecules. Liquid is bonded to liquid. Solid is bonded to solid. But gases are not bonded to other gases. So for example, if I had an ice cube, ice is made of water. Here's one water molecule. Here's another water molecule. Here's another water molecule. If I was to demonstrate to you that the water molecules were bonded together, I would have hydrogen bonds connecting them. Those red lines are hydrogen bonds. Now, when those bonds are really, 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 really strong, this would likely be in the solid state. If I were to weaken those bonds, the bonds are still there. They're just weaker. That would be a liquid. But when you have a gas, you have heated up water, in this case water, so high that the bonds have actually broken. And so now there is nothing holding one water molecule to another water molecule. This is why water molecules are capable of going anywhere, and not just water molecules, but gas molecules of any substance, oxygen, carbon dioxide, nitrogen, whatever. Gases are not bonded to other gases. So when you're not bonded to something, they're free to go wherever they want. And they move in all random directions. Now, another tenet of the kinetic molecular theory is that when pressure, which is P, increases, V, which is volume, decreases. So there's a visual on your PowerPoint I'll draw for you. Here's a container. And inside the container are gas particles. All these little circles are gas particles, okay? And these gas particles are just going in some just random direction. That's what these arrows are indicating. They're just bouncing around all over the place. So this is what we call the plunger. It can be pushed down. These are gas molecules, which is a type of particle. This is in volume 1. Volume is the amount of space occupied. If I were to ask you what is the traffic volume right now on Dale Mabry, it's probably not that bad. It's 10:30. Most people are at school. Most people are at work. The traffic's probably not bad. You go out on Dale Mabry about 7:30, 8 o'clock, it's bad. You go out in the highways, you go out on 275 around 5 o'clock, you're going to be in a parking lot. So volume is space occupied. This volume looks pretty high, but let's change that. Here's our second container, and here's our plunger. Jade, has the volume inside this container increased or decreased? The volume has decreased. So what has happened to the pressure? That's right. The pressure inside the container is increasing. Because I moved the plunger down to lower the amount of space occupied for the gas to inhabit. This is the plunger. And when I reduce the amount of space where the gas is, I've decreased the volume. And because I decreased the volume, I've increased the pressure. That's right. So if I like I used to have a tennis ball around here somewhere, I would squeeze the tennis ball, and as you squeeze the tennis ball in your hand, it gets harder and harder and harder to squeeze it more and more and more, because what you're doing is the gas particles are basically bouncing around so much that they're pushing against you. So when I take a tennis ball in my hand, I squeeze and I squeeze and I squeeze. Eventually, I can't squeeze it as easy as I could when I started. It's because the pressure inside the tennis ball is a lot higher because I've decreased the volume. So let's continue with the kinetic molecular theory. The kinetic molecular theory is predicated on several factors when it comes to gases. All right, the particle size. You can have big gas particles, you have small gas particles. Gas particles are separated from each other by empty space. They have the most room for compression or condensation. Because gas particles are so far apart from each other, this is an important one. They experience little to no attractive forces or repulsive forces. They're going so fast and there's so much space between them that they really aren't going to be attracted to each other. Hey Derek, did you wave hello to that really cute girl you saw on the interstate when you were driving 80 miles an hour and she was going 80 miles an hour in the opposite direction? No, you didn't, because you didn't even see her because you were going too fast and she was going too fast. Good story. They're not attracted to each other or repelled by each other because the particles are going so fast and there's so much space between them, they're not going to be attracted or repelled what's really at all. Next will be particle motion. Gas particles are in a constant random motion. There's nothing to attract them, so there's nothing really to influence them except for two things. So if you have your notes, obviously you have the answer to my question I'm about to ask you. What are the only two things that gas particles could really, what are the only two things that could influence where a gas particle goes? They're not attracted to each other. So they're not going to be drawn towards one particle or repelled by another. But as they're just bouncing around like a crazy ping pong ball all over the place, what are the only two things that could influence the direction in which they move? What's that? No, pressure and volume. I'm talking about when they're bouncing all over the place, Jade. What are some things they could come into contact with that will influence which way they're going to bounce and ricochet and hit? No. Okay, the container is one. When they collide with the container, so direction is influenced by one, the walls of the container. If you ever like to play pool, billiards, the direction in which the ball is going to go depends on how it hits the wall, what angle it hits the wall. Pool is all about geometry, 100% geometry. So if you want to hit that, you want to have the perfect shot, you have to line up your angle just right. What else think about pool? What else do the balls hit besides the wall of the container? Each other. Now, just because they're colliding into each other doesn't mean that they're attracted to each other. You guys have likely bumped into a person or two in your life. You need to go, oops, excuse me, will you marry me? Doesn't really go like that. You just, oh, excuse me, go on with your day. All right. Collisions between particles are elastic. I believe this is a vocab term for you. Okay, an elastic collision is where two particles crash into each other, but neither of them loses energy. In fact, energy is transferred from one object to the other. So if you were to run into someone, rather than come to a screeching halt, if you were gas particles, you would have object A and object B. They would crash into each other, and A and B's energy would be transferred to each other, and they would just keep on going. They don't lose energy. Now, if you were to play, if this rule applied to games like billiards, which is pool, you hit the 8 ball, and rather than the 8 ball slow down and the white ball slow down, they're just going to keep going and going and going no matter what. They're always going to keep bouncing around, hitting other balls. That's called elastic collisions. No energy is lost. And in that, kinetic energy can be transferred. Okay. And then the last factor, guys, is going to be particle energy. Number 3, particle energy. There are 2 factors that determine the energy of a particle. Hey, Max, let's say you get into a car accident. Let's see if you can, if this is a proper analogy, I might be way off base here. Max, if you were to get in a car accident, what 2 factors of the car accident can really determine how damaging or deadly the accident could be? Okay, that's 1. Well, in physics, we don't say speed. No one says speed. We say velocity. Velocity is measured as meters per second squared, or meters per second per second. What else, Max? How fast you're going in?
If I was wearing a seatbelt.
Let's just say the actual, not the occupants. I'm saying the actual vehicles. Yeah, the mass. How big the vehicle? How much mass the vehicles had? Mass is measured in grams or kilograms. So kinetic energy which is KE, is equal to 1/2 mass times velocity squared. Yeah.
If one object hits another object and it gives all its energy to the other one with no energy lost, is that still elastic?
Yeah.
Okay.
And by the way, velocity, guys, is not only how fast you're going, but in the direction which you're going. So you would have to say you were going 20 meters per second to the right, or you were going 20 meters per second squared to the right, or you're going 50 meters per second up. So it's always not only how fast you're going, meters per second, but in which squared, but which direction you were going. I remember that being drilled into my head in physics class. And then second to last, let's see. All particles do not have the same kinetic energy, so therefore, they do not have the same velocity, so they do not have the same kinetic energy. All particles do not share the same velocity Therefore, all particles do not share the same kinetic energy. KE, kinetic energy. All right. Yes, Kevin.
Why does direction matter?
I don't know. I can't tell you. In physics, let me see if I can dig deep into my brain here. When we were learning that was like the first week of physics. Because I think you have to take gravity into effect. If you say you're going up, then that means you're going against gravity, and that's going to affect your velocity. If you're going with gravity, that's not going to affect your velocity. So you have to indicate, gravity is, I think, 9.18 meters per second squared. That's how much gravity influences an object. That's the gravity here on Earth, at least. That does influence the velocity. I'm pretty sure that's why you have to indicate the direction. Next, Derek, I want you to do me a favor. I want you to slap your hands together. I want you to rub your hands together really fast, really quick. What's happening is going faster.
They're getting hotter.
Oh, right. So temperature is the big one. Let's see. Where's my phone? Hey, Siri, what is the temperature outside?
1 moment.
It's because it's trying to get on the school Wi-Fi, which is trash. Here we go. Hey, Siri, what is the temperature outside?
It's 64 degrees right now.
What? I didn't think it was going to be that cold. Now, it said 64 degrees. Notice I said temperature. Temperature is the average kinetic energy, which means right now, outside, if it is 64 degrees, that means that there are areas of the atmosphere where we're at here in Tampa where it is warmer than 64 and it is cooler than 64. 64 is the average. It's an average of all the different particles. So there are gas particles moving in our atmosphere right now. They're moving at a velocity that indicates it is about an average of 64 degrees, which means that there are gas particles probably higher up in the atmosphere that are moving a lot slower because it's colder up there. They're moving at a cooler temp, which means they're not moving very fast. And then there's particles down here in the surface which are moving a lot faster, which would indicate a warmer temperature. That would be a greater kinetic energy because they're moving faster. The faster things move, the more energy there is. The faster Derek rubbed his hands together, the warmer it got. When you're driving your car, there's a heat gauge on a lot of your dashboards. The faster you go, the more the heat gauge tends to show an increase in heat. And the colder you go, the more it slows down. When you're driving your car, one of the worst things you want to do is, as soon as you turn off your car, is to play around with the insides because everything is really hot because everything's been moving. You got to let it cool off for a while. The faster things get, the hotter things get. And temperature is just an average of everything moving in the atmosphere. All right, let's talk about compression and expansion. Carson, you had a question or something?
No.
So I'm sure you all already knew this. Compression is a reduction of volume. If you took a balloon and you were squeezing it between your hands, you're compressing it. You're reducing the amount of space that balloon is taking up. Air is highly compressible. In fact, it is the most compressible state of matter. Why? And this is something I had to bring up to my AP kids a lot for bio, so definitely remember this. Air has, when I say air, I mean gas. gases have the most space between them. For example, let me come over here real quick. Let's say here's a gas. Ready? Look at all the space between the particles. Here's a liquid. Not a lot of space. And then here's a solid. You can squeeze gases a lot and get a very, very, very small amount of gas. What if I told you that the same amount of particles I just put in that solid are the same amount of particles in there, in the gas? The only difference is the space that is in between them. So gases are highly, highly compressible. If you had a balloon filled with concrete, imagine this, you had a balloon filled with concrete, you probably couldn't squeeze it. It's gonna be solid. But if you had a balloon filled with air, you can squeeze it a lot. You might be able to get both sides to touch each other because there's just so much space between gases, between the particles. So there are large amounts of space between gas particles. The presence of empty space allows particles to be compressed. And forced closer together. Which means you're going to have a reduced volume. So if you take a look at this jug of water I have about half a gallon of water here. I'm going to try to squeeze the bottom. Can't really go anywhere. That's as much as I can get. Now I'm going to squeeze the top. A lot more. I was able to put, because there's nothing but air there, I could push into it, forcing the gas particles to have more collisions with the wall. And that will increase the pressure. I want to see if I can find my tennis ball. I got it maybe on my desk somewhere. Yep, there we go. Okay. Here you go, Max. Catch. I want you to try to make both sides of the golf ball or the tennis ball touch each other. Show us. Don't hold it like that. Oh. Now let me show you guys what he just did. He started off like he was fine. Like, here's Max. Oh. Why did you struggle here and not here?
Because there's more air.
Okay, so this is a pretty big volume. There's a lot of space between the gas particles. So what he's doing is he's reducing the volume. If he's reducing the volume, what's increasing? The pressure. The gas particles are literally bouncing back at him with a greater velocity. So as he's pushing more and more into the tennis ball is pushing back because the gas particles are pushing back. I think I got it. There we go. Here, Max. Oh, both sides touch. Can you do it? Maybe.
Yeah.
All right.
I got it like barely. Not bad.
So let me ask you guys this. Why is it bad to overinflate your tires? Does anybody know? You guys are new drivers. Arshawn?
Because if like they compress, they'll get a chance to like pop.
Yeah. If you fill up connect the dots, cause and effect. If you put as much gas as your tires can hold, where there's like literally no space left between the particles, they're this close to each other, you go over a speed bump, you go in a pothole, you go over a railroad track, your tire is going to push in from that bump or that obstruction, hole in the street or a railroad track or something. And when something pushes into your tire, like a railroad track or a speed bump or something, is there any place for the gas particles to go because you overinflated it? No, the only place for them to go is out. blow out. That's why you want to leave a little bit, you want to have a specific pressure in your tires so that when you do go over those things that tend to be all over the roads around here, is that the tire will be able to push in and the gas particles will just compress a little without blowing out your tire. It's like overinflating a balloon. If you put too much air in a balloon, there's nowhere for the air to go but out. So if you had an overinflated balloon and you pushed into it just a little bit, pow, it's going to blow up. But if you had a normally inflated balloon, you push into it, it will eventually pop if you put a lot of force into it. But if you're just like this, it's not going to pop. But if you overinflate it, one little poke, blows up. All right. Let's see what I want to do here. All right, let's go to diffusion and effusion. Yeah.
What's in the space between the gas particles or any particles?
An empty void.
Okay.
Space. It's like outer space. There's nothing. A vacuum. Okay, remember that gas particles are not attracted to each other, so they just fly by each other. These are a couple terms on your vocab, I believe. Diffusion is the movement of particles from one area to another. Now, I want you all to think back to freshman bio. Naturally, do particles flow from high concentration to low or low to high? High to low. Think of a fart in the elevator. It's going to go from a high concentration, which is your butt, to everywhere else in the elevator where the fart did not exist. You go from high concentration to low concentration. Now, here's a new term, effusion. You ever notice when you buy birthday balloons, you get some helium in them about a week later? They're not floating as well as they were. Effusion is not low to high. That's the first thing students think of. Oh, that's low to high. No, that's diffusion too. That's called active diffusion, where you go from low to high. Effusion is diffusion through a little hole. Despite how balloons can hold gases like helium, there are microscopic, like molecule-sized openings where slowly over time, the gas can escape. And those balloons start to lose their helium, which is what's caused them to be lighter than air. And this is going to lead us to Graham's law of effusion. The rate of effusion of a gas is inversely proportional to the square root of its molar mass. Now that sounds scary, but I think that when you guys see it, it's going to be actually pretty simple. Rate of effusion is going to be equal to 1 over the square root of the molar mass, or grams per mole. Another way to think of this is rate of gas A over rate of gas B will be equal to the square root of molar mass of B over the molar mass of A. That's an easier way to think of it, I think. Now, which one's going to be A and which one is going to be B? That's one of my biggest problems in math was. How do I know which one is A? How do I know which one is B? How do I know whichever one is actually mentioned first? When you're reading the word problem, A is the first substance mentioned. B is the second substance mentioned, and then you just flip them and do the square root. So let me do an example problem for you. If you could please get out your calculators. This is actually pretty simple. I want you to do it yourself. I'll work you through it. This is going to be a Graham's law problem. You will need your calculators every day this semester. Ammonia has a molar mass of 17.0 grams per mole, period. Hydrogen chloride HCl has a molar mass of 36.5 grams per mole. What is the ratio to their diffusion rates? Okay. I'll let you guys get all caught up. What's that? Diffusion. It's going to be the same thing, Nicole. Yeah. All right. I'll let you guys get caught up. So let's see a couple pens moving. So your known values. Colby, what are the knowns here?
Ammonium and hydrogen chloride.
Their values would be 17 grams per mole and 36.5 grams per mole. Your unknowns is the ratio of diffusion rates. Okay, so as I said, if you guys look here, it says the rate of A over the rate of B is equal to the square root of the molar mass of B over A. And I told you, how do you determine which one is A and which one is B? Whichever one is mentioned first. So Jade, what substance was mentioned first in the word problem? Ammonia or hydrogen chloride? Okay, so ammonia, NH3, we're going to call A. And hydrogen chloride, HCl, is going to be B. So normally you would do 17.0 grams per mole over 36.5 grams per mole. But remember, we're going to flip it, and we're going to do the square root. The square root of 36.5 over 17. Can you guys do that for me? The square root of 36.5 over 17. 1.47. So the ratio of diffusion is 1.47. Here's what I really want you to say, and I really want you to know this. If you gave me 1.47, I'm not going to say you're wrong. But if you did this, I'm going to say you're super right. 1.47 to 1. That calculator doesn't tell you that. It just told you 1.47. But when you're doing ratios, that's why I did this. Ratios can always be something to 1. So we're going to say 1.47 to 1. That's the ratio. Yeah. If all things being equal, a rate of 1 would be how fast this is going. This is 1.47, so this is diffusing slower than what you would normally say for a gas, because it's higher than 1. Anything that's less than 1 would be diffusing very quickly. And anything that's diffusing more than 1 is going faster, or excuse me, slower.
Is it like a unit or is it just?
There are no units of measurement here. No.
Yeah.
All right. I think I want to stop there. I have one more page for you guys, but I think that's a good place to stop. Tomorrow we're going to start gas pressure. And that'll be the second day for gases. Yeah.
So the higher the number, the slower the diffusion?
The higher the number, the slower the diffusion.